Okay, I want to talk a little bit about resonance. So, resonance structures are two or more Lewis structures that have the same skeletal formula but different electron arrangements. So, this is when you can have multiple valid Lewis structures that are representing a particular molecule. So when you draw a Lewis structure, it's just giving an idea of kind of how things are connected and where the valence electrons are. And that helps us then to understand something about the three-dimensional arrangement of things. And that way we can then start to make predictions about physical properties of things. Um, and so when we draw a Lewis structure, it's helping us get to that. And you don't actually need to know every resonance structure if something can have more than one Lewis structure in order to figure out three-dimensional information and understand all of that. Um, but sometimes it's nice to know that, yes, there is more than one representation for this particular molecule, or one of those is more stable than the other. So if you're trying to deal with that kind of stuff, what you need to know is the real molecule actually exists as an average of the resonance structures. And so um, the true structure isn't any one of the Lewis structures. Now, if you only have one possible Lewis structure for something, then it is giving you a pretty true indication of what's going on. Whereas if you have something that you can draw more than one valid Lewis structure, then not any one of those is really the true structure. The true structure is some sort of mixture of those or average. Um, but it depends on, are those structures equally valid or not? So if you have equally valid or equivalent structures, meaning they all have essentially the same stability, then each is going to contribute equally. Okay, meaning you can think of it as kind of a true average of the structures. Whereas if you have non-equivalent structures, then the true one is going to be like the best. Okay, so sometimes you can draw multiple Lewis structures and one of them is just much more stable than others. Then that's the reality of what the compound really exists as. Okay. So the resonance structures are just different ways to represent the same molecule. So it's essentially just electrons kind of shifted in a little bit different location, but the connectivity of the atoms, like what's in the center and what's on the outside, that does not change. Okay? If you change what's in the center and what's on the outside, then you have a completely different compound. So when you're trying to draw resonance structures, you shouldn't be moving the atoms around, only the electrons. So let's look at some examples to help understand this a little bit better. So here I say draw three valid Lewis structures for CO2. Okay, so there's actually three possible Lewis structures. So we're going to go through the basic procedure for drawing a Lewis structure. Okay, and so if you follow these steps in order, it should get you to a valid Lewis structure. Okay, you may not initially find the best one, but that's okay. Valid is what you need, meaning it needs to have the right number of electrons and everything needs to have an octet, unless if you're talking about hydrogen. Okay, um, so if we go through these steps, we have carbon. Carbon has 4 valence, and then each oxygen, which we have 2 of, has 6. And so if we add that up, that means we have 16 total electrons to work with. And so then we need our skeletal structure. And in this case, carbon should be in the center. The way the formula is written kind of helps you know that because it's written first. Also, Carbon's less electronegative than oxygen. And oxygen is just one of those elements that typically only will be in the center if it's with hydrogen or fluorine. So if it's kind of forced to be there. Okay, so now we have our skeletal structure. We want to distribute our remaining electrons, which we have 12 left over because we've used 4 for these 2 single bonds. And so what I can do is I can add 3 lone pairs to this outer oxygen and 3 lone pairs to the other outer oxygen, because we always want to start on the outside. That's going to make your life the easiest. Now, if we do that, we've used up our other 12. Right now, there are 16 electrons on this structure, so I can't add more dots to fix any octets that aren't there, okay? You can't do that. So all you can do is move around the electrons that you have, okay? So what we can do is we can take from one of these oxygens to fulfill the octet of the carbon that only has 4. But there's a couple of ways we can do this, okay? So what I could do is I could take a lone pair from this oxygen, which would bring that carbon up to 6, and I could take another pair from this other oxygen, and that would bring the carbon up to 8 then, and that would give me a structure with carbon double bonded to 2 oxygens, and you would still have 2 lone pairs on each of those oxygens. So we'd still have a total of 16 electrons, and now we would have 8 electrons on each oxygen and 8 electrons on the carbon, okay? Remember, you're kind of double counting each of those bonds. You're counting them for the carbon and the oxygen that they're bonded to, okay? Now, we could have done something a little bit different. I could have, let's say, instead of taking from the oxygens on both sides, just taken from one. So let's say I took this lone pair and shared it with carbon and this lone pair and shared it with carbon instead, okay, instead of that other one. And so then I would have this oxygen on the left that's triple bonded to the carbon and the other one's still single bonded. So that one would still have 3 lone pairs since it's still, single bonded. That, there we go. But this other oxygen would still have just 1 lone pair, okay? And so that still has 16 electrons in the total structure, and everything has an octet. So that's another valid Lewis structure. Now there's one more option. I could, instead of sharing from the oxygen on the left, share from the oxygen on the right. So say I took both pairs from it. And if I did that, I would have a triple bond to the right-hand oxygen and a single bond to the one I have on the left. And the one on the left would still have 3 lone pairs. And the one on the right would only have 1 lone pair left. And so that structure also has the 16 electrons it needs, and everything has an octet, okay? So all 3 of these structures are valid Lewis structures for carbon dioxide. Now, sometimes you're asked to draw all the valid Lewis structures, you know, all these resonance structures. Sometimes you're just asked for one. So if you were just asked for the Lewis structure of CO2, you could draw any one of those 3 and they're fine, okay? But with that, those 3 aren't actually equivalent structures. And so this is a case where you actually have one of them that's better than the others, and that's actually this first one. We're not going to go into exactly why that is, but it just has to do with the fact that your oxygens have the same electronegativity as one another, right? They're all the same element, and so they have the same pull on electrons. So they're going to share electrons similarly. And so you're not going to have one of them pulling more electrons and only being single bonded, and another one releasing, more electrons and being triple bonded. They're going to have kind of an equal pull on those electrons, so that distribution is going to be even. Now, if you had different outer atoms, then it may be true that an uneven bonding would make sense. But in this case, it wouldn't. So those are three valid structures. In this case, the top one's the best structure. So the true structure of carbon dioxide really is, carbon double bonded to two oxygens. Okay, now let's look at another one. Let's do COCl2. So if we have COCl2, we count up our valence, we've got 4 for carbon, 6 for oxygen, and then 2 chlorines, each of them is 7. And so that totals to 24 electrons. So then we need our skeletal structure. So we have carbon, oxygen, and chlorine. Carbon's written first, so it's probably in the center. Also, if you think about oxygen, generally is not going to be in the center, neither is a halogen like chlorine, unless if those are the only things in the structure. So carbon is definitely going to be in the center. And so then carbon is bonded to an oxygen and 2 chlorines. So I have that. I've used 6 electrons, so I have 18 left. So if I start filling octets on my outer atoms, fill an octet on my oxygen, on my chlorine, and on my other chlorine, that uses up my remaining 18 electrons. So now I have 24 electrons on this structure. So last step, does everything have an octet? No, it does not. Your carbon only has 3 bonds, which is not an octet. And so you need to share from something that has an octet. Okay, so we actually have 3 options here. I could take one from this oxygen and share. That would give me carbon double bonded to this oxygen, still single bonded to these chlorines. And those chlorines would still have their 3 lone pairs. And the oxygen then would only have 2 lone pairs. So that structure has 24 electrons, but now everything has an octet. So that would be a valid structure. But I can do some other things. I could have, instead of sharing from that oxygen, I could have shared from this chlorine to the carbon instead. So if I would have done that, I would have had a double bond to that chlorine and a single bond to the oxygen and the remaining chlorine. So the oxygen and the chlorine that are single bonded would still have their 3 lone pairs, and this chlorine would only have 2 of its lone pairs left. And so again, we have 24 electrons in that structure, and everything has an octet. So that's another valid structure. But we can do one more thing. Instead, we could have shared from this chlorine down here at the bottom. If we had done that, we would have carbon double bonded to that chlorine and single bonded to the oxygen and the remaining chlorine. So the single bonded ones would still have their original 3 lone pairs, and the one that now is double bonded would only have 2 of its lone pairs remaining. And that one also has 24 valence electrons, and everything has an octet now. Okay, so all 3 of these are considered to be valid Lewis structures. Now this one, you have, a different stability, okay, for these 3 structures, and that's because your outer atoms aren't all the same. If they were all the same outer atoms and the double bond just shifted between the same atom, then it would be equally stable and the true structure would be an average of those. In this case, you have the double bond either with an oxygen or with one of the chlorine atoms, and they have different electronegativities, oxygen and chlorine. And so you're going to have a different favorability for having, lone pairs versus double bonds in this. And what it turns out as is, in reality, this one with the double bond to the oxygen is the most stable And that's because oxygen on its own has two unpaired electrons, so oxygen does kind of favor being double bonded, whereas chlorine has 7 valence on its own, and so it only has one unpaired, so typically chlorine favors only having one bond, and so that can kind of help you determine that. There are other ways you can assign formal charges. We're not going to go into that, not in this video. That's something for, if you're going a little deeper in. So we won't do that part. Let's do a couple more examples. Make sure you kind of got the idea of how you go about finding different valid structures. Now I've got NO2 minus, so the nitrite ion. So if we have nitrite ion, we've got 5 valence for nitrogen, and each oxygen gives you 6. And then we have a negative charge, meaning we've got 1 extra. And so let's see. We've got 18 total electrons. And we've got NO2 minus. So oxygen doesn't like to be in the center, so that means nitrogen's going to be in the center. Also, nitrogen's written first, so that's usually your hint that that's in the center. We have 2 oxygens coming off of it. And so we've used 4 of our 18 already. We've got 14 to go. And so if I add octets to the outer atoms, that uses up 12 of my 14 remaining. So I have 2 more, and those go on the center. So I put a pair on the center. Now, once I do that, I have my 18 electrons, and then you need to check for octets. Each oxygen has an octet because they have 6 from their lone pairs and 2 from the bond. So the nitrogen's got 2 bonds, so that's 4, and a lone pair, which is 2, so it's only got 6. So the nitrogen's lacking here. So I need to share from something that has an octet, meaning one of the oxygens. So I could take from this oxygen over here and share with the nitrogen. If I did that, I would have a double bond to that left-hand oxygen and a single to the right. So the one on the right would still have its 3 lone pairs, but the one on the left would now only have 2 of its lone pairs left. And the nitrogen still has, its lone pair that it started with. So now your nitrogen has 3 bonds in a lone pair, which is an octet. So this, we put our negative charge on it, that is a valid Lewis structure for NO2 minus. But I could have done something a little bit different. I could have taken a pair from this other oxygen instead, and it would give me a different structure. So that would give me a double bond to the one on the right, a single on the left. I would have 3 lone pairs still on the left, and I would only have 2 remaining on that one on the right, and still a lone pair on the central nitrogen. So that's still 18 total electrons, but now everything has an octet. So I place my charge, and that would be another valid Lewis structure for NO2 minus. Okay, and so these are both valid. Now these two have the same external atom, and so in one of them it's got a double bonded oxygen and a single bonded, and on the other one that switches, and so the single and double bond are swapping between the same element, so these actually are equally stable, and so the true structure is some average of this, meaning in the true structure of nitrite there's not a single and a double bond, there's 2 bonds that are somewhere between that, so you have like 2 1.5 bonds. And so kind of the key though is first you need to be able to draw these structures, and don't worry so much about are they equally stable, which one's more favorable. Just worry about, can I get these structures? Can I find when there's more than one possible? And then draw those. Okay, we'll do one more example of SCN minus. This is thiocyanate ion, sorry. Thiocyanate ion. So first let's calculate the total number of valence electrons, and that is 6 for sulfur, 4 for carbon, and 5 for nitrogen, and we have a negative charge, so that's 1 more, so that's 16 electrons. Now this one can kind of trick people because, like I was saying before, usually what's written first is in the center. But when it's three different elements like this, when it's just three atoms and it's three elements, they'll write it in the bonding order. So when they write SCN, it really is S bonded to C bonded to N. Okay. If they, because they'll jumble those if you have a different bonding arrangement. Because some of these that are like this can bond in multiple ways. So that's why they do that ordering. So we'll just take it because it's given as SCN and happily write it that order because they wrote it that order. And then we've used up 4 of our 16 electrons, so we have 12 to go. So I can put 3 lone pairs on my sulfur, 6 of those 12, and 3 lone pairs on my nitrogen. That's the other 6 that were remaining. And so now I have 16 electrons, but we have a problem. We have the carbon that is lacking. Okay, so we need to share 4 more electrons with carbon, meaning we have really multiple options. I could share 2 from each side. Okay, so if I shared 2 from each side, I would have sulfur double bonded to carbon, double bonded to nitrogen, and I would still have 2 lone pairs on each of those. Okay, and so that's 16 electrons. Everything has an octet, and I would put my charge on there of minus. So that's one option. I could share 2 from each, but I could also instead share, say, only from the sulfur. If I shared only from the sulfur, I would have a triple bond to the carbon and then a single bond to the nitrogen. And my nitrogen would still have its original 3 lone pairs, and the sulfur would only have 1 lone pair left. And then I'd have a negative charge still. Okay? And so that's another possibility. On the other hand, we could share from just the nitrogen. If we shared 4 from the nitrogen, then I would have sulfur single bonded and then triple bonded carbon to the nitrogen. So my nitrogen would only have a lone pair left, my sulfur would still have its original 3 lone pairs, and I would have that overall negative charge. So all 3 of these structures have octets on everything and a total of 16 electrons. That's what's needed for structures to be valid. They need to have the right number of total electrons, and they need to have an octet on everything. Unless if you have hydrogen, hydrogen does not get an octet, okay? So these are our 3 resonance structures for this. Now this one, I guess I didn't actually say that there's 3, but there's 3. So a lot of times if you're asked to draw the Lewis structure of something, if you're just asked for the Lewis structure, you draw 1, okay? If you're asked for resonance structures, there should be multiple. And a lot of times you're not told how many. You just have to figure out how many can I come up with that are valid. And so in this case, if I had just asked for a Lewis structure, you could give me any of these 3 and that would be fine. If I asked for the resonance structures, you would give all 3. Now this one is a little bit trickier if you were trying to figure out which one's most valid, because they're definitely not all equally stable because you have 3 different elements and different bonding in all of them. And these 3 different elements, they're going to have different electronegativities. So there's going to be a different favorability for how many electrons something pulls towards it. Okay. And so you have to base it off of some electronegativity comparisons. We're not going to go into that, but that's how you would determine it, is to use electronegativities and figure out which one favors kind of pulling electrons more towards it. Okay, so I think that's enough resonance examples, at least to get you started.